Welcome to part 5 of our Agile training program, Engineering Practices. Agile success depends not only on how teams plan their work, but also on how consistently they apply sound engineering discipline. Engineering practices help teams turn ideas and requirements into reliable, integrated, and demonstrable outcomes. They create a shared approach for managing uncertainty, maintaining quality, coordinating technical work, and learning from actual results. For multidisciplinary engineering teams, these practices strengthen collaboration across all streams. In this part, we will explore the engineering mindset and disciplined ways of working that support predictable delivery and continuous improvement. Let us begin part 5, Engineering Practices. Welcome to part 5 of our Agile training program, Engineering Practices. Let us understand the topics that we will cover today. First, Agile estimation helps teams assess the relative effort, complexity, and uncertainty involved in completing work. Second, planning metrics provide visibility into capacity, progress, delivery trends, and the overall health of the sprint. Third, risk planning helps teams identify uncertainties early and address critical technical, safety, schedule, supply chain, and integration risks. Fourth, quality practices ensure that reviews, testing, defect management, and continuous improvement are built into every sprint. Finally, integration discipline enables teams to combine their work regularly, manage configurations, and maintain release readiness. Together, these 5 practices help engineering teams deliver reliable, integrated, and demonstrable outcomes with greater confidence. Let us begin part 5, Engineering Practices. A product backlog usually contains more work than an engineering team can complete within a single sprint. Estimation helps the team assess the available work and select a realistic sprint scope. In EV development, even a seemingly small requirement can involve several engineering disciplines. For example, adding a low battery warning may require BMS data, communication signals, control logic, operator display behavior, diagnostics, testing, and documentation. Estimation creates a structured discussion about the complete scope before the team commits to delivering it. This discussion can reveal hidden dependencies, unavailable information, unfamiliar technology, integration effort, and validation requirements. However, an estimate is a forecast based on the team's current knowledge, not a guarantee of delivery. The objective is therefore to create a reliable shared understanding of the work before the sprint begins. Let us have a quick look at what is a user story. A user story describes who needs a capability, what they need, and why it provides value. The standard format is, as a user, I want a need so that I achieve an outcome. For example, an EV operator wants a low battery warning to return or recharge before power is lost. The story encourages conversation, while acceptance criteria confirm success through measurable conditions. Story points express the relative size of the complete work required to satisfy the definition of done. The team considers effort, complexity, uncertainty, and dependencies. The Fibonacci scale uses 1, 2, 3, 5, 8, and 13 points. Larger values are spaced further apart because uncertainty normally increases with the size of the work. For example, a low battery warning may require BMS data, control logic, operator display behavior, diagnostics, and integration testing. The team may compare this with a simpler display text change and estimate it at 5 story points. Large stories should be clarified or split before entering a sprint. Another method of estimation is T-shirt sizing. T-shirt sizing provides a quick relative estimate when backlog items are still at a high level. The team compares items as extra small, small, medium, large, or extra large. The size reflects complete effort, complexity, uncertainty, and dependencies, not only implementation work. For example, changing a display label may be extra small, while adding a charging icon may be small. A low battery warning may be medium because it includes BMS data, display logic, diagnostics, and testing. Integrating a motor controller or battery pack becomes larger because more disciplines and dependencies are involved. Poorly understood work should be clarified, split, or investigated through a technical spike. Team estimation begins by clarifying the user story, acceptance criteria, and expected outcome. For a low battery warning, the team reviews BMS data, control logic, operator display behavior, diagnostics, and integration testing. Each engineer then estimates independently and reveals a planning poker card simultaneously. This prevents the first opinion from influencing everyone else. Different estimates are valuable because they may reveal hidden interfaces, missing tests, dependencies, or different interpretations of the definition of done. The team discusses these assumptions and estimates again when necessary. If uncertainty remains high, the item should be clarified, split, or investigated through a technical spike. Once shared understanding is reached, the team records the estimate and its assumptions. Team velocity becomes more useful when it is observed across multiple comparable sprints. At the beginning, the team has limited delivery evidence, so the gap between forecast and actual completion may be significant. After each sprint, the team reviews completed story points, unfinished work, blockers, dependencies, and estimation assumptions. This evidence improves the team's understanding of its capacity and delivery patterns. The forecast is then adjusted using actual experience rather than initial assumptions alone. Across sprints 3, 4, and 5, the difference between forecast and actual velocity gradually reduces. By approximately sprint 6 or sprint 7, the two values begin to converge. This does not mean velocity must continuously increase. It means the team is becoming more accurate at forecasting what it can realistically complete. Agile estimation is not expected to be perfectly accurate from the first sprint. The dartboard on the left represents early estimation. Results are widely scattered because the team has limited historical data, uncertain dependencies, and several untested assumptions. At this stage, the difference between estimated and completed work may be significant. With every sprint, the team compares its estimates against actual results. Through inspection, adaptation, and calibration, it learns how complexity, integration effort, interruptions, and technical risks affect delivery. After several months, historical velocity and team experience provide a stronger basis for forecasting. This is represented by the dartboard on the right, where the results are more tightly grouped around the target. Over 1 year of repeated sprints, feedback and learning should gradually reduce estimation variation. The objective is not perfect prediction. It is increasingly reliable forecasting based on evidence rather than guesswork. Sprint capacity represents the realistic amount of work a team can undertake during a sprint. The Scrum Master facilitates this calculation with the team, starting with gross availability based on the number of members and working days. The team then deducts planned leave, statutory holidays, and partial working days. New members may join, but onboarding, mentoring, and reduced initial productivity must also be considered. Capacity should also account for support activities, vehicle trials, training, audits, production issues, and sprint ceremonies. Finally, the team considers whether the required skills and specialists are available for the planned work. In this example, 60 gross person days are reduced by 18 days of constraints, leaving 42 person days of available capacity. The process is to check the calendar, confirm availability with the team, calculate capacity, and then select realistic sprint work. Remember, capacity is an availability forecast, not a productivity target. Now that Agile estimation is complete, let us move to the next topic, planning metrics. Planning metrics help teams understand their capacity, monitor sprint progress, and identify emerging delivery trends. They provide useful evidence for forecasting and informed decision-making without becoming measures of individual productivity. Let us explore how these metrics support transparent and responsible Agile planning. A burn-down chart begins with the planned work and shows how much work remains throughout the sprint. However, a perfectly smooth downward line is not mandatory. Engineering work often completes in steps following design reviews, hardware availability, integration activities, or testing. A flat burn-down line may indicate blocked work, backlog items that are too large, delayed testing, or work status that has not been updated. A burn-up chart provides a different perspective by displaying completed work and total scope separately. This makes scope changes clearly visible. For example, if a battery warning requirement gains an additional diagnostic or safety condition, the total scope line increases. Burn down is useful for monitoring remaining work, while burn up is generally clearer when sprint scope changes. These charts should initiate a constructive technical planning discussion, not a search for an individual to blame. A responsible sprint dashboard presents several related signals instead of relying on a single completion percentage. Sprint-wise team data can reveal recurring patterns such as overcommitment, increasing carryover, aging blockers, and unstable quality. Capacity and velocity must remain separate because capacity describes future team availability, while velocity records historically completed work. A reduction in completed story points does not automatically indicate lower team performance. It may result from reduced capacity, added scope, supplier delays, integration failures, defects, or unavailable test facilities. Therefore, cumulative trends should be interpreted across several comparable sprints with written explanations for significant variations. This helps leadership understand the engineering context behind the numbers. The dashboard should therefore track team sprint delivery history, not individual performance history. Individual story point totals and completion percentages are not reliable measures of productivity. Story points describe the relative size of team-owned work and must never be used to compare individual engineers or different teams. Now that planning metrics is complete, let us move to our next topic, risk planning. Risk planning helps engineering teams identify uncertainties before they affect delivery. It enables teams to prioritize critical risks, test assumptions early, and prepare suitable mitigation actions. Let us explore how effective risk planning improves confidence and supports successful sprint outcomes. Risk in Agile development is any uncertain event or condition that may affect the sprint goal. For an EV team, one risk could be a delayed motor controller or BMS, preventing planned integration. Another is cross-team misalignment, where mechanical mounting, electrical wiring, CAN communication, and software interfaces do not work together. A third risk involves safety and performance. For example, overheating, traction loss, or unsafe stopping. Assumptions can kill projects when they remain untested for too long. Risk-based planning therefore brings uncertain, safety-critical, dependency-heavy, and long lead work forward. The team should identify the risk, plan mitigation, test early, and use the learning to improve future decisions. Risk-based planning considers uncertainty, impact, and available mitigation when selecting engineering work. During quarterly or release planning, teams identify major architectural, safety, supplier, facility, certification, and integration risks. Long lead items such as battery cells, motor controllers, connectors, sensors, custom harnesses, and machined components may require decisions before detailed design is complete. During backlog refinement, broad risks become specific backlog items, technical spikes, prototypes, supplier actions, interface reviews, or validation activities. Sprint planning determines which risks must be reduced during the coming sprint and what evidence will demonstrate that reduction. The team monitors risks during the daily scrum and reviews them through sprint reviews and retrospectives. The sprint backlog manages the required work, while the risk register maintains formal visibility, ownership, exposure, response, and status. Risk-based backlog ordering considers product value, urgency, uncertainty, dependencies, and the cost of delaying important learning. This does not mean that every high-risk item automatically becomes the first priority. The team must balance risk reduction with value, readiness, and capacity. A technical spike is a time-boxed investigation designed to answer a specific question and produce evidence or a decision. For a new battery system, the team may first validate the BMS protocol, current capability, thermal response, and controller interface on a bench setup. Dependencies such as hardware, supplier firmware, test equipment, interfaces, and vehicle availability must also be visible. Long lead components require early action because procurement delays may affect several future sprints. The objective is to determine whether each assumption is validated, rejected, or remains uncertain. Order work for the earliest valuable learning, not simply the earliest visible output. Risk management follows a shared cycle of identifying, assessing, responding, executing, verifying, and updating each risk. The whole team contributes, but every significant risk must have a clearly identified owner. Developers identify technical integration uncertainty, propose mitigation actions, perform tests, and report objective evidence. The product owner balances risk exposure with customer value, urgency, dependency, and delivery priorities. The Scrum Master supports transparency and helps remove organizational impediments. Engineering leads and technical authorities decide or escalate architecture, interface, safety, and compliance matters. Safety, quality, project, and supply chain representatives own specialist risks and escalate matters, but on team authority. Risk records must show the owner, exposure, response, due point evidence, and status. Relevant actions belong in the sprint backlog, connecting execution with engineering evidence and the controlled risk register. A completed backlog item closes a risk only when evidence shows reduced or formally accepted exposure. Now that risk planning is complete, let us move to our next topic, quality practices. Quality practices help engineering teams build reliability into every sprint through disciplined reviews, testing, and defect management. Let us explore how these practices support consistent quality and continuous improvement. Quality in Agile development means building the right solution correctly and proving it through objective evidence. For an EV, quality begins with the materials. Low-grade steel or incorrect material thickness can cause deformation or structural failure under payload and terrain loads. Wiring quality is equally important. A damaged wire, incorrect gauge, or poor crimp can create voltage drops, overheating, and intermittent electrical faults. Fastener quality also affects vehicle reliability. A weak bolt, incorrect tightening torque, or missing locking feature may allow a critical joint to loosen under shock and vibration. Therefore, quality must be built into every sprint. The team should specify the requirement, inspect the implementation, conduct the necessary tests, and record the evidence. As the quote reminds us, quality is not an act, it is a habit. For an EV, quality means not merely working once, but operating safely, reliably, and repeatedly. Quality must be created throughout every sprint, not inspected only after engineering work appears complete. In EV development, no single discipline can confirm product quality independently. A completed CAD model, software build, or tested harness may still fail during vehicle integration. A battery warning, for example, depends on reliable BMS data, communication, control logic, display behavior, diagnostics, and calibrated thresholds. Quality built-in begins with clear requirements, continues through peer review and verified implementation, and ends with integrated testing. The definition of done must require reviews, test results, configuration records, documentation, and traceability. This exposes defects early, reduces rework, and produces objective evidence in every sprint. Quality is created during engineering, not added after engineering. Vehicle confidence grows through reviews and testing at progressively higher levels. Design and peer reviews examine requirements, interfaces, tolerances, safety implications, and testability before defects move downstream. Code reviews assess correctness, error handling, diagnostics, security, and coding standards. Relevant unit tests should already be implemented and passing before review. Unit and component tests verify software functions, circuits, harnesses, mechanical parts, controllers, and calculations. Integration testing confirms that connected components exchange correct power, data, commands, forces, and diagnostic responses. System testing verifies the complete EV against performance, safety, environmental, diagnostic, and operator requirements. Automated tests improve repeatability across builds, interfaces, and regression checks. Physical inspection, engineering judgment, environmental testing, and vehicle trials remain essential. Test locally, integrate progressively, and verify at vehicle level. Release notes are a controlled record of what changed, what was verified, and what users need to know about a release. In this example, EV version 2.3.0 is based on candidate configuration UGV-RC-03. Engineering release notes provide technical detail and traceability. They capture configuration and version identifiers, interface and calibration changes, defects fixed, known limitations, verification evidence, and upgrade or rollback instructions. Customer-friendly feature notes communicate the same release differently. They explain what is new, why it matters, how to use it, visible limitations, and any safety or support guidance. For example, this release introduces obstacle stopping, improves the low battery warning, fixes CAN reconnection, and records that GNS denied return remains unavailable. Both documents must remain accurate and consistent, but their level of detail should match their audience. A release is not complete until its changes, evidence, and limitations are understood. Now that quality practices is complete, let us move to our final topic, integration discipline. Integration discipline helps engineering teams combine their work regularly, manage configurations, and identify system-level issues early. Let us explore how disciplined integration supports reliable and release-ready outcomes. Integration discipline combines multidisciplinary engineering changes in a controlled, repeatable, and verifiable manner. It covers interfaces, versions, automated builds, progressive testing, defect resolution, and evidence. Integration starts before vehicle assembly, when teams agree on requirements, assumptions, interfaces, and test conditions. In EV development, one feature can cross mechanical, electrical, electronics, software, communication, diagnostics, and calibration. A battery warning depends on BMS messages, controller logic, display behavior, thresholds, firmware, and test configuration. These discipline outputs must converge into one identified and controlled vehicle baseline. The baseline records the exact hardware, software, calibration, configuration, and test environment. Integration evidence then supports an informed release decision and feeds defects back to the responsible teams. The objective is a result that can be rebuilt, tested, explained, and audited. Progressive integration moves from fast virtual environments toward increasingly representative and expensive physical testing. Model-based simulation evaluates control concepts, vehicle dynamics, energy behavior, and boundary conditions before hardware is available. Software-in-the-loop tests compiled control logic against simulated inputs, interfaces, and automated scenarios. Hardware-in-the-loop connects a real controller to a simulated vehicle for timing, diagnostics, and controlled fault injection. A subsystem bench then introduces real batteries, controllers, harnesses, sensors, and actuators. Vehicle integration confirms complete interaction under representative power, communication, mechanical, environmental, and operator conditions. Each stage follows a repeated cycle of integration, testing, recording, correction, and reintegration. Use the earliest environment capable of answering the engineering question. A candidate configuration is a proposed, version-controlled set of compatible items selected for integration, testing, or release. For an EV vehicle, this configuration may include the drive controller hardware, vehicle control software, motor controller firmware, steering calibration, chassis drawings, and the vehicle bill of materials. Each item must have a clearly recorded version number. These selected items are combined into a single candidate baseline, such as UGV-RC03. Before integration, the team confirms that all items are selected, their versions are captured, dependencies are compatible, interfaces are defined, and no configuration conflicts remain. The workflow is simple. Select the required items, verify their compatibility, integrate them, and then test the complete vehicle configuration. Candidate configuration prevents teams from testing an unidentified mixture of components. The key principle is, if you cannot identify the version, you cannot reproduce the result. Release readiness depends on knowing exactly what was tested, which evidence supports it, and who approved it. The candidate configuration must identify hardware, software, firmware, calibration, drawings, BOM, tools, and test environments. Matching evidence includes build results, review records, test reports, traceability, defects, and approved deviations. The readiness gate confirms that the configuration is complete, required tests passed, critical defects resolved, and approvals recorded. Developers integrate changes and provide evidence, while the integration engineer coordinates builds, deployment, and baseline assembly. Engineering leads govern interfaces and technical acceptance. Quality, safety, configuration, and project teams verify compliance, versions, dependencies, and release status. Results from a different configuration cannot be silently reused. If the configuration or evidence cannot be reproduced, the baseline is not ready for release. This concludes Part 5 of our Agile training program, Engineering Practices. We explored Agile estimation, planning metrics, risk planning, quality practices, and integration discipline. Together, these practices help engineering teams plan responsibly, manage uncertainty, build quality into every sprint, and deliver reliable, integrated outcomes. Thank you, everyone, for attending this session. We hope you found the training useful and enjoyed the learning journey.